Hi, everyone. Thank you very much for the invitation to speak. It's great to be part of spreading the excitement about causal inference. So, a brief bit about me. After 15 years in a permanent academic faculty position, I left to become a freelance data scientist. And I've spent the majority of my time working as part of PyMC Labs, where we help companies turn data into insights in order to drive business decisions. Now, before we kick off with the slides, I would just say I became a father just 2 weeks ago. So I promised to do my very best to convey why you should be excited about Bayesian causal inference despite my extreme level of sleep deprivation. So let's dive in. In this talk, I'm going to focus on this map of uncertainty and um, uh, causality. So on the y-axis, we're climbing the ladder of causality with statistical associations at the bottom and causal reasoning at the top. On the x-axis, we have the degree of uncertainty quantification with traditional frequentist or point estimate type of approaches on the left and Bayesian methods on the right. So I'm going to be a little bit bold and just place much of data science in the um, bottom left of this plot. Um, so there are well-known and widely used methods and software packages that we can use to do a whole bunch of things, including predicting outcomes, forecasting into the future, and generating insights from your data. And we can live down in this corner and be perfectly happy for a while. However, uh, taking a purely statistical approach really restricts us in the kinds of questions that we can answer. So fortunately, Judy Poe, amongst others, have written extensively making the case for climbing the causal ladder. So I don't necessarily need to repeat all of these arguments here. But in short, um, if you interpret purely statistical inferences in a causal manner, that can lead to entirely unexpected effects once you or somebody else starts to intervene in the system by acting in the world, for example. Secondly, causal approaches are definitely required in order to answer these wrong 2 and 3 interventional and counterfactual questions. So we have heard about some of these today. Examples of interventional questions would be things such as how much should I spend on advertising in order to maximize new customer signups? Or what level of discount should I give in order to maximize profit? Counterfactual questions would be of the flavor like, what would have happened if I'd spent my marketing budget differently? Or what would the UK's GDP be now had we not voted for Brexit? So we are already seeing people, companies, and scientific disciplines venture upwards up the causal ladder to address questions which require causal approaches. The slight kind of drawback or the difficulty of this is that it does require a lot of upskilling. Let's say if you've got a traditional data science or statistics type of background, there are loads of new causal concepts to learn. But the good thing is that there are a whole bunch of different software packages out there. And we're also starting to see the emergence of books on causal inference focused towards practitioners, which are more kind of software heavy rather than maths and theory heavy. Now, I think that what will happen, my prediction, is that many people will stay on the left-hand side of this space, sticking with traditional frequentist or machine learning type methods. And that is absolutely fine. However, We are seeing a meaningful migration eastward. So many are finding that Bayesian methods are very well suited to their problems. Many are finding that Bayesian methods offer advantages over traditional approaches. So let me just give a very brief primer about what Bayesian inference is, if you're not already familiar. So one way of explaining it is that it is essentially the optimal way to revise your beliefs about the world in the light of new evidence. So that's a really important and useful thing. It also avoids some interpretability problems and some of the strict assumptions that are associated with frequentist statistical methods, for example. And it also allows you to quantify your level of uncertainty. And this is really crucial when we're making high stakes decisions. Very importantly as well, it allows you to leverage your valuable personal or institutional domain knowledge into models via either the DAGs that describe the causal story of your data or the Bayesian priors themselves. And finally, in the kind of Bayesian sphere, it is more standard practice to build bespoke models that fit your exact problem rather than trying to shoehorn your problem in to fit into a prepackaged statistical solution, for example. However, my contention for today is that combining the two and taking a Bayesian causal inference approach is particularly compelling. So, in short, the payoff is that we can answer the kinds of questions that we really care about, and they're the ones that we need to be at the top of the ladder for. And we get all of the benefits of the Bayesian approach that I just outlined. But I would say, in addition to that, I think there's extra synergy. So, for example, both Bayesian and causal approaches embrace subjectivity. Some people are very tempted, understandably so, to remain fully objective, and they want to just let the data speak for itself. But both Bayesian and causal approaches kind of take a slightly different stance and say that really you as a practitioner need to bring your subjective knowledge about how the world works, the data generating process, to the table. And Bayesian approaches also kind of say that we can do better in terms of inferences by incorporating prior knowledge, which is inherently subjective, quantitative, but subjective in nature. So if you buy that argument and you're interested in the top right-hand area of our chart, the question is, what tools can we get there? Now, this is not a systematic, wide-ranging survey. I'm going to be quite selective, focusing on PyMC. Now, PyMC is a Python-based, I'd say very mature at this point, open source probabilistic programming language, and it has a very large and diverse user base. Traditionally, it has been seen as a purely Bayesian statistical inference library, but we are finding that we only need to make some minor modifications to enable it to address Bayesian causal inference questions. We are also finding that climbing up the causal ladder is perhaps a little bit easier if you already have a bit of Bayesian background, because you already would have acquired a bunch of concepts, not by no means all of them, but many of the concepts that you need for causal thinking. So we, as in the open source PyMC and more broadly probabilistic programming language community, are really starting to embrace causal concepts to help make Bayesian causal inference more accessible to everyone. We're also building open source packages. So Causal Pi is one that I released a little while ago, which is built on top of PyMC, which lowers the barriers even further to give quick, easy access to a subset of causal inference problems revolving around quasi experiments. So it has features that help you do things like synthetic control, difference in differences, regression discontinuity, and these kind of things which you'd broadly label as econometrics, perhaps. Now, there are, of course, other libraries, but I'm focusing on where my expertise lies. So in the rest of the talk, let me just give you a brief run through of how we might use Bayesian causal inference to address a very simplified problem. So I'm going to talk about this very generically. So let's think about a particular treatment. So a person can either receive treatment or they can not receive the treatment. And what we really want to understand is what is the causal effect of receiving the treatment. So this, if you want to think of something concrete, it could be things like, does running an ad campaign increase customer signups? Or you could ask, does drinking coffee increase productivity? Does offering customer discounts decrease customer churn, for example? So one of the ways that we could approach this from more of a statistical background is simply to plot the distribution of outcomes that we see for those people who did not receive the treatment and for those people who did receive the treatment. Now, we could run a frequentist or a Bayesian t-test and start to put some numbers on this to say how different are these distributions. But for this fictional data set, it's relatively clear that exposure to treatment is associated with increased outcomes. So can we say that the treatment improves the outcomes? Well, probably not. Probably not. Because again, this is a simple scenario. Many more complicated ones exist, but in this one, we perhaps didn't account for the full data generating process that really underlies the data. So the conclusion that we came to through a purely statistical approach could be completely wrong because we failed to take into account this full data generating process. And in this case, we have a confounding variable, and this can be disastrous if you try to interpret statistical associations causally. So what can we do? We could use PyMC, for example, to translate what we think about the data generating process into code. So the exact lines of code here aren't important. They won't be in the test at the end. But essentially what we're doing is specifying what variables listen to what other variables. And because we are taking a Bayesian approach, we're also specifying prior beliefs over the strengths of these relationships. So the first step that we might take is to essentially run our Bayesian statistical inference, and we might obtain posterior distributions such as what we can see here. So we would essentially estimate the unknown parameters that govern the strengths of the relationships between the confounder, treatment, and the outcome. And because we are taking a Bayesian approach, rather than just getting a single number, a point estimate, we get a full Bayesian posterior distribution that describes the relative credibility of different values. Now, because this example is using simulated data, we can compare the model estimates with the true values used to generate the data. And that allows us to estimate how well this process is working. So looking at the one example that we've got here in the top left, we can see that the posterior distribution given in blue essentially represents a pretty accurate estimate of the true value of 1, which is given here in orange. And we don't need to go through all the others, but we essentially see for this example that that is the story that unfolds for the other parameters in our model. But we want to do something causal. And one possible causal thing we could do is to calculate the average treatment effect. And if we wanted to distill this into a single sentence, we estimate this by basically asking, looking at the difference between what we believe the outcomes would have been if we intervened and gave everyone exposure to the treatment versus what we believe the outcomes would have been if we intervened and gave nobody the treatment. So we can do this in PyMC. We saw in the previous talk an example of the do operator. So PyMC recently obtained a do operator as well. And what this does is to take in a kind of a code representation of the structural causal model. You tell it what intervention you want to make, and then it spits out a new mutated model. And that represents your interventional distribution. And we can use MCMC in order to generate samples which approximate this distribution. Now, we can do the same thing for the case where we have no treatment, and then essentially just do the subtraction. So compare these distributions in order to come up with our estimated average treatment effect. And the plot here shows our full Bayesian posterior over the average treatment effect. So again, not only do you you can get a point estimate if you like. So let's say it's minus 0.0022, so very small. You get an entire distribution of credible ATE values. And we can see again, because I simulated this data where there's actually no direct causal influence of the treatment upon the outcome, we can see that by using this Bayesian causal approach with relatively few lines of Python code, we can get a pretty good Bayesian estimate. So our previous kind of statistical approach of, let's say, we could have done a t-test by just comparing distributions, observational distributions, was essentially meaningless. Taking a causal approach allows us to get a much better estimate, and taking a Bayesian causal approach allows us to quantify our level of uncertainty with the full posterior distribution here. And in general, knowing your level of uncertainty is really important, like I say, when we're making high stakes decisions about whether or not to roll out an expensive intervention. And in this particular case, we would probably decide not to do that because it has no causal impact on our outcome of interest. So in summary, we fully expect there to be a mass migration up the causal ladder as more people, companies, and scientific disciplines embrace causal inference. But we see many advantages that hopefully I've kind of outlined to pairing both causal and Bayesian approaches. And this is in terms of making the journey slightly easier, and also just gaining all the benefits of the Bayesian approach, not least the principled quantification of uncertainty. So we, as in the PyMC open source community, are working towards facilitating more causal inference to lower the barriers of accessibility to causal inference. Now, if you would like to know more, then we at PyMC Labs offer corporate training and consulting services using both Bayesian and causal inference methods. We've had the pleasure of working with some really fantastic companies and help them solve really hard but high impact business problems. And if you're interested in getting more of a flavor of Bayesian and causal inference methods, then my personal website has a set of recordings and also a list of the various kind of pedagogical, didactic writings that I've got on the topic. So thank you very much. Happy to answer any questions if we have time.
Thank you. We have a bit of time. So, I will start first just answering people asking, is it okay to share public screenshots from all your great talks, like your bands and others? I don't think anyone will be against, so please do, and tag the event, and it will make us extremely happy. So I have a question for you. So, um, to use PyMC or causal pi, it is necessary to specify the formula that links each variable in the DAG. What can we do if we do not know what this relationship looks like? James, I hope I pronounced correctly, asks.
Yeah, so I mean that is tricky. So yeah, in PyMC, you do essentially have to describe not only the relationships, so the DAG, in terms of what is connected to what, but you also have to go further and essentially define a full structural causal model where you specify the nature of the relationships between those variables. So I don't have one short, easy answer for this, but it's going to basically be a mixture of starting simple. So very often people look at linear relationships. So you're effectively doing path analysis type stuff. You can introduce various nonlinearities if you have mixtures of like continuous versus discrete variables and so on. So I think this is the real answer, though, I think, is probably some kind of hard model building work, which involves exploring your data set and bringing domain knowledge about these relationships to the table. And you never know if you're correct.
Okay, and obviously Bayesian is a big topic and causal is a big topic. How do you think we can address the challenge of learning two approaches at the same time?
Yeah, so you're right. And I don't want to kind of shy away from that fact. So if you kind of start outside the Bayesian sphere and you start outside the causal sphere, then you could argue that you've got double the amount of stuff to learn. Now, but I believe in you. I believe people, you can do it. Yeah, what I would say is that personally, I'm kind of overjoyed if people take more of a causal approach, even if they stay like traditional. That's great. But yeah, we do see these advantages. So we kind of think that the payback is worth the effort. That's just been our experience.
Yeah. Brilliant. Thanks a lot.